Welcome everybody to our optimization in Oslo seminar. We're very happy to have Professor Brendan Keith from Brown University visiting us today in person, so semi-virtual talk. Brendan is going to talk about adaptive sampling for constraint optimization under uncertainty. So Brendan, please.
Thank you, Thomas. Okay. So before I start, I want to thank you all for coming, and Thomas for giving me the opportunity to speak here and being such a wonderful host. I think I'm looking around the room and I've met most of you. I'll be here for a couple more days, for those of you I haven't met yet. So Thomas said this talk is about adaptive sampling for stochastic optimization. So what I'm going to do in this talk, I'm going to first introduce the adaptive sampling algorithms for stochastic optimization with deterministic constraints. I'm then going to state some theorems that we've proved about these algorithms. And then finally, I'm going to use these algorithms for a sophisticated building design optimization problem. So in this talk, a lot of the problems that I'll be dealing with I don't know if this doesn't seem to be working too well, so maybe I'll use this to direct you. So in this talk, most of the problems I'm going to be dealing with look something like this. So we have an objective function that's written as a risk measure applied to a random objective function you can sample from. C is a random variable. R, as I said, is a risk measure. If you don't know what a risk measure is yet, you can just think of the expected value operator. And C, where we're actually performing this optimization over, is a constraint set. So if C is just the entire space, one of the representative algorithms people use to solve this type of problem looks something like this. So you take the iterate you are at currently, xk, and you form a sample average of gradient samples of the objective function that you can compute. You agglomerate them to a sample average gradient, and then you advance your update in the negative direction of those gradients. So this is the well-known stochastic gradient descent algorithm. And in this talk, the main takeaway is that if you can we can construct checkable conditions on the size of this sample set, S of k, that enforce a balance between the stochastic error, the statistical error, and the optimization error. So these conditions look something like this. And if you satisfy these conditions, then the sample size will grow at a controlled rate, something like this. And it will deliver the same convergence rate when you actually apply it to your problem as if you were using the underlying deterministic algorithm. So actually first order rate in terms of iterations. So in this talk, I'm going to talk about cases where the constraint set is both defined implicitly and where it's defined explicitly. And I'm going to try to convince you that using this type of algorithm is going to reduce your computational burden. It's going to make you need to form or compute fewer samples in the long run in order to get the same error. And all of this theory is going to build up to get to a sophisticated building design optimization problem where we've managed to reduce the cost by about 60%. And this is a very expensive optimization problem. To put it into absolute numbers, the reduction in computing cost, if a company were to solve this problem on Amazon Workstation or something like that, on Amazon Workspace, and rent computing time, this would be a reduction equal to $60,000 of actually renting out space on that server. And to implement this, to make this change in their loop, comes down mostly to an if statement that you can run that checks this condition. So I like to call it the $60,000 if statement. But in order to get to that if statement, I need to tell you a few things about stochastic optimization. So stochastic optimization at times looks something like this. Expected value of f. We have random variables sampled from a fixed measure mu. I'm going to advance too fast there. So this type of problem shows up a lot of the time in machine learning. It's well studied there. It's a very hot topic right now. And one of the popular algorithms, same one I showed a few slides back, stochastic gradient descent. but they typically use a fixed sample size. So its sample size is typically very, very small. This makes the every iteration quite cheap. As I said, it's used extensively in machine learning. One of the things I want to point out about it is that the step length is a heuristic most of the time. It's very hard to study step length choices for this type of problem. There's hundreds of papers written about it. I don't really want to get into it in this, but it is something to keep in mind. It's cheap per iteration, lots of iterations, heuristic step lengths. So I do some work in machine learning, but my primary driving focus of my research is usually to solve scientific or engineering problems. And they can also look like the ones I showed previously. Maybe in this case, you have uncertainties coming from the environment that you're studying. So if you look on the right here, the environment, what we're trying to do is we're trying to optimize for a thin shell structure. So we have uncertain loads that are going to be applied to this shell model. And though you don't see it in the picture, there's also uncertainty in the thickness of the shell. So there's modeling uncertainty and environmental uncertainty coming through the loading. We want to find the optimal configuration of this shell. You can see the algorithm moving here to find the optimal design that's going to maximize the stiffness. So its constraints will appear in this problem. This is what typically separates it from machine learning problems. We have constraints. So often, if you look at this setting, we don't want the design to go into the floor. Or in this particular setting, we also don't want the ends to stay in a parallel plane. So those are relatively simple constraints. And more complicated constraint that also appears here is we have a surface area constraint. So this is basically saying that we want to make sure that we use a fixed amount of material in this case of configurations. So if there's simple constraints, we can have them defined explicitly. Sometimes we have access to a projection operator onto the constraint set. And if we do, we can modify the previous algorithm and write it like this. So we would take the update, we would advance just inside these parentheses, like normal gradient descent, and then we would, before defining our new update, we would project onto the constraint set. So this is called projected gradient descent or stochastic projected gradient descent. And you can proceed just as you would before. You can use a fixed number of samples, very small, cheap, per iteration, lots of iterations, heuristic step lengths. And then finally, we might be in a situation where we don't have access to the projection operator. So there are many different algorithms you can study to deal with this type of setting. The one I'm going to focus on is called augmented Lagrangian. What you're seeing on the right side here is an example I'll come to later. It's topology optimization, trying to find the optimal distribution of material to either absorb or release heat into an environment. But in augmented Lagrangian, it's a two-stage algorithm. So the first stage, you solve an optimization problem, and then you advance a Lagrange multiplier, sort of like gradient descent. So as I've written it, both of these iterations are deterministic, but what you would do if you were to apply adaptive sampling, or if you try to solve this problem where f is written as the expected value of some function, you would use a stochastic algorithm to solve the subproblem in this case. And then everything I said before applies. So you can solve the subproblems, for instance, with stochastic gradient descent, and then all of the implications would carry over. So in this talk, I want to go beyond that setting and address a few of the concerns that come from that simple algorithm. So first, you're going to try to overcome this sublinear and very slow rate of convergence with respect to iterations. Though I don't really want to focus on it, this will also help us overcome heuristic step length choices. Typically, what you can find is using step length rules that come from the deterministic analysis work equally well when you apply adaptive sampling to the optimization problem. And then we're going to keep in mind here that we're probably solving very expensive problems. Every sample is involved solving a PDE or something like that. And we may, as the number of samples increase, have to solve a lot of samples in parallel. But if we are solving on a large machine, we can exploit the parallelism of the environment. We can solve those problems in parallel. Adaptive sampling will let us, in that way, populate the machine and exploit all these resources in a very cost-efficient way. And I want to do all of this and build out a theory that doesn't just rely on a projection operator, and that will take us eventually into augmented Lagrangian. So if we just go back to the simple case where we have access to the projection operator, everything's going to look like this. We do a projected stochastic gradient descent step. However, we're going to start with a very small number of samples. So in this example, we start with 10 samples and we grow to 10 to the 4 samples throughout 100 iterations. And the algorithm will, on the fly, determine how many samples we need in order to balance the two sources of error, one coming the variance in the gradients that we're computing, and the other source of error is really just how close we are to solving the problem, the optimization error. So the sample size will grow. We'll decide how to change it based on a posteriori error estimates. And we'll show that if you use a fixed step length, then you would recover the rates of convergence equal to the rates of convergence of the underlying deterministic algorithm. So I think at this point, the general idea that the thing that we're trying to accomplish here should be clear. What remains to be fleshed out is how do we actually do it? What do we actually check? How do we quantify this error and how do we balance it? So about 10 years ago, in the unconstrained setting, a very useful variance test was proposed by Nosedal and people in that orbit. And it looks like this. So on the left-hand side, we have the sample we have the variance in the gradients, and we try to bound that by the norm of the gradient. So if the vector function is strongly convex, then you can show that the right-hand side also bounds the optimization error. And that way, you should think of this as saying, we're making sure that the variance in the gradient is bounded by the same thing as what bounds the optimization error. Therefore, they're both going to decay at the same rate. You can prove that that will give optimal convergence rates. However, I'm not going to do that here. That was done quite a while ago. But I want to convince you that this is a sensible condition. So let's assume that this actually does converge. But what would happen to the sample size in this case? So if we converge to an optimum, then the right-hand side should go to 0. And the only thing that can make the left-hand side to go to 0 is by increasing the number of samples. The variance is going to be determined by the size of the set SK that creates that actual sample average here. So it's going to, by design, force the number of samples to increase. However, I want to point out that this test will fail, and it's remained open to figure out how to generalize it to the constraint setting for quite a while. But I'll show you how to fix it in the next slide. It will fail if you have constraints. And the reason it will fail is because you typically converge to a boundary of your constraint set, and therefore the right-hand side gradient of f in this test will not go to 0. Okay, a second thing I want to point out before I show you how to solve this issue or how to generalize this properly is that you don't actually have access to a lot of things that appear in this test. So for instance, you don't actually have access to the gradient of f, okay? If you did, then why would you even compute f sub sk? So what people do in practice is they use a population variance on the left-hand side, and they substitute the sample average of the gradient on the right-hand side. And this in practice works just as well, but most of the analysis is done for the idealized norm test. And then you use an approximate test in practice. Okay, so in the idealized setting, if you have constraints, in our recent paper, we propose a new generalized norm test, which looks a lot like the old one. The left-hand side is exactly the same. The right-hand side is, however, a little bit different. We have something we've shoved in there, R of xk, which we call the reduced gradient. If the problem is unconstrained, this reduced gradient reduces to the true gradient. And the reduced gradient, there's a number of ways you can think about it. But the way I'll propose for the sake of this talk to think about it, it's like a directional derivative in the space of your design update. So you would advance your iterate forward in the idealized setting. So here, this is the step you would wish to take. You subtract where you were and you divide by the length of your step size. That's the reduced gradient. And then this, even though we do not have access to the true gradient of f, we can, just as before, write down a practical test that you can use in your code. So on the left-hand side, just as for the original norm test, you can use the population variance. And on the right-hand side, you just have the norm of the difference between your update, your current update and your next update, and divided by the length here. So what I'm doing on this part of the slide is I'm just taking all of the terms of importance, putting them to one side, defining this to be a random variable nu, and the test reduces to seeing if this random variable is less than 1. This is just a convenience because it makes everything fit into this slide here. So the test will pass if random variable is less than 1, and what we'll do is we'll keep the size of the sample set the same. We'll resample, but draw the same number of samples. If it fails, we increase the size of the sample set based on the rate or the ratio at which we've failed the test. It's very simple, very easy to implement. So we just have an if statement in the regular stochastic gradient loop. And implementing this test problem, you see a very controlled rate in the number of samples. So this is all well and good. We've also proved that this will deliver the optimal convergence rate that you would, in expectation, that you would see in the deterministic algorithm. So if your adaptive function has Lipschitz derivatives, it's strongly convex, and you satisfy the generalized norm test at every iteration, then in expectation, you converge Q linearly, definition of which is written right here. That's the best you can really hope for this class of algorithms, and we've gone a little bit further. So we show if you relax the strong convexity assumption to choose convex only, you get what reduces to the best you can hope for convergence rate in expectation of this algorithm. And even in the non-convex setting, you get a weaker mode of convergence. So this originally appeared on arXiv about 2 years ago. And 3 weeks later, one of the top groups in the country posted a very similar result. And well, they proved similar results to these first two. They did not prove this case. This may not be the most interesting. I think that the thing I want to say here is that it made it a little bit difficult to publish this. We were both similar ideas appeared at the same time. Finally, ours, as just recently accepted to IMA JNA. I also want to say that we're now working with that group. So the rest of this talk actually is a collaborative research with Raghu Balapragada, the second author of this paper here. Yeah.
What did they do then? I mean, did they have some kind of reduced gradient, or what did they use for the upper bound?
They have reduced gradient, but the expected value appears somewhat like slightly different place.
So they have the same difference quotient.
Yeah.
Okay.
Yeah. So their test. I don't have it written on these slides, but it's very, very similar. So ours, we have a reduced gradient, and we would have used the true F here.
Mm-hmm.
Theirs, they have an expected value outside of the norm.
So
they would look at an average over all of the possible updates.
And do they also have a practical test?
And then they also have a practical test. And actually, the practical test is exactly the same as ours.
Okay.
So their analysis starts from a different idealized test, but in practice, it leads to exactly the same thing. Okay, so I said, now I'm going to step into the territory where we don't have access to the projection. And I know this is an optimization seminar, but at the same time, I know that a lot of people in Simulink aren't optimizers. So I'm going to introduce some things that maybe optimization people would find basic, but I think is going to be educational. So I'm going to tell you what augmented Lagrangian is. I'm going to just derive it for you in a few slides. So, and to start off, I'm going to start with the very, very fundamental result you would probably see in first class of the first course on nonlinear optimization, written right here. So if you have a function with Lipschitz continuous gradients, then you have a bound that looks like this on the function values. And it turns out that gradient descent itself derives from minimizing the right-hand side of this inequality. So to explain to you what I mean by that, you can minimize what I've written. What's inside these braces is just the right-hand side of this inequality. You minimize this, you write out the first order optimality condition, you get this equation here. If you rearrange it, you get the gradient descent rule. Now, if you look up here, we're using a linear approximation of the function that we're minimizing. So one could suppose, well, what if we improve that approximation? What if we actually replace that linear approximation here by the true function? Okay, for right now, this is just a hypothetical, but if you go through the motion, derive the optimality condition, you get something which I will call proximal point. Some people call this implicit gradient descent, and you can see why maybe some people call it that, because it looks like gradient descent, except gradient descent would have xk inside the argument of the gradient of that. So the reason I'm even introducing this in the first place is that augmented Lagrangian can be thought of as a proximal point method. It's not obvious, but I'll show you why. Okay, so you would start off with a saddle point problem that looks like this. In our case, f will be the expected value of something, and g will be a deterministic constraint. And you write it in saddle point formulation with Lagrangian here. And this would come from introducing this Lagrange multiplier lambda. So now let's just say I want to apply the proximal point method to that Lagrangian. Okay, so I am doing that on the Lagrange multiplier. So I have to add this quadratic term. And if you can always do this, but under the appropriate assumption. So if you would say quasi-convexity in X and quasi-concavity in lambda, and you can alternate the max and the min, you can solve the inner maximization problem. This will tell you how to, this will give you this update rule for lambda. And solving the minimization problem accordingly to find X, which you actually sub into this formula, involves minimizing what's called the augmented Lagrangian for fixed lambda. Okay, so that's why I just added all those things I said about proximal point. And then ultimately you have these two stages. So you solve the primal problem of the augmented Lagrangian with the step length beta, which came from the proximal point. And then after solving that subproblem, you update the Lagrange multiplier with a step length of size beta, and then you loop. Okay, so if the primal problem is the expected expectation of something, you can use adaptive sampling on the subproblem. Now, typically, you don't solve the subproblem exactly, you solve it to some tolerance. And control that tolerance, and that will give you sort of the most an efficient augmented Lagrangian algorithm by dialing down that tolerance at a correct rate. And this makes the analysis somewhat pseudo-deterministic, because you have control over the tolerance that you solve those subproblems at. And by doing that somewhat pseudo-deterministic analysis, we're able to prove this result. It's not the strongest result we think is possible, but we're also somewhat convinced that it's probably the strongest result that we can get out of a proximal point-based analysis. And maybe a new analysis would be necessary to get something stronger than this. So what we show is that under appropriate assumptions, regularity of Lagrangian, then we get sublinear convergence in expectation of the feasibility error. So I'm neglecting the optimality error in this because we get control over that from the subproblems. We can solve the subproblems as accurately as possible. So that's already implicit. We already control that. The only thing we have to actually analyze is the feasibility error, and that will converge at some linear way. Yeah.
Is that in finite dimensions?
Yes. Finite dimensions only.
For infinite, you would probably need more than just positive definite. You need uniformly positive definite, probably a Hilbert space or something like that.
Yes.
Yeah.
This is a good point. However, we have applied it to an infinite dimensional problem just blindly, but this first example is very much finite dimensional. Okay, so this is logistic regression with constraints, which is not something you always see, but I should probably point out that this is an important setting of logistic regression or any type of problem of this nature. So what I want to say here is that when you're doing regression with biased data, usually the approximator that you end up incurring will have that data built in. So for instance, if I'm a bank and I want to create a decision-making device that will take in a bunch of categories for an applicant for a loan and just determine whether or not to give them the loan, and I'm basing that on a pool of data that's based on mostly an affluent white population, it may have certain biases built in that could lead to trouble for me down the road. Now, there's a recent paper that came out that you can control for this type of bias by introducing equality and inequality constraints. So what we have done is studied a logistic regression problem with this type of constraints. They're somewhat random vectors just to verify the algorithm. And we're using a data set that has nothing to do with banking decisions. It has something to do with mushrooms. But it lets us verify the algorithm. So we see quick convergence of the objective function. You can see controlled growth of the sample size and also controlled decay of the feasibility error. The next slide is something that I find is closer to my own research interests, is topology optimization. So here I'm showing topology optimization, as I said before, of a thermal compliance. We're trying to find the optimal distribution of material in the space that we're being heated from the top, and heat is able to be released through this opening at the top. We're being heated uniformly inside, and heat cannot escape through the boundaries. You get to design something like this. This is a 2D example, but this can be extended to 3D. So here what you're seeing is recent work by one of my co-authors on this project, Boyan Lazarov, and he also optimized the 3D thermal compliance here for a very hot LED light. So this is a heat exchanger that will release the heat that the light produces into the ambient environment. So the problem we've set up has to do with additive manufacturing, which when you actually try to build a device like this, or a heat exchanger, because of the very interesting shapes that it can take on, you often use a 3D printer or something like that. And that will introduce uncertainties into the actual built device, the geometry of the built device. So we are trying to accommodate for that uncertainty during the design process. And the way we do that, so these are the equations here. We have diffusion, we have zero heat here, uniform heating inside, no flux on these parts of the boundary, and we have a diffusion tensor with a sigmoid function. So I'm not going to explicitly write out what the sigmoid is defined in terms of. What I want you to know is that there is a random field built into it. So this will try to vary the geometry of the built device. We have also constraint on the volume, and then we optimize here. So if we would just taken the expected value of the random field used in this problem, and then done the deterministic optimization, we get a design that looks something like this here. A lot of little leaves branching off from the design. However, introducing the uncertainty gives us a much more conservative design, which is interesting in its own right. But from the algorithmic point of view, we can also see adaptive sampling working very hard and efficiently to solve this problem. So the algorithm decides that we need only 10 samples to about just past the third of the way through the entire optimization process. So this is saving us quite a lot right from the beginning. And then it decides to increase it. When we do a Lagrangian update, we decrease it. And then from there, we start actually really converging to the design, and it grows until we get to an appropriate error and then stop the process. We see convergence of the objective function here. And what I want to point out on this panel here, this is the ideal setting for convergence of the reduced gradient with adaptive sampling. So you see linear convergence in expectation and controlled variance throughout the entire optimization process. And that's making sure that all the error, the optimization error and the statistical error online. So this is just one study, or two studies maybe I've gone over in total with adaptive sampling, and there's many more things one could look at. So there's recent work on sequential quadratic programming by my co-author Raghu that I encourage you to check out. There's a lot of interest, but not much work yet on dealing with probabilistic or chance constraints. Everything so far that's been done in the community that deals with constrained optimization, it uses deterministic constraints. There are outstanding challenges in dealing with the chance constraints setting, but a lot of interest in looking at that. And then finally, and I'll finish the talk talking about this mostly through an example, dealing with other risk measures is also of interest here, the other things than the expected value. Okay, so with other risk measures, I'm going to mostly motivate why we do this here. So the rest of the talk will be mostly about this building optimization problem. Now, I used to live very close to San Francisco, and if you live close to San Francisco, one of the things that you see in the local news pretty much every couple months is a large article, usually front page, about this building, the Millennium Tower. And the reason it kept making the news and consistently does is that it was this $100 million construction project, and it is tilting. It's built downtown San Francisco. Every few months, a big gust of wind comes by, some extreme weather pattern. It's a city. Nobody's quite sure. Well, something happens and it tilts like a few inches in a few days, and then a new article is written. And this is a huge concern because obviously they don't want it to fall over, and they also, the people that build it don't want to deconstruct it because they've invested so much. So what is going on? There's a massive project to extend the foundation of the existing building to make up for this and to catch it before it starts to fall over. So one could say, well, this was poor engineering decision, but it was. I would guarantee that this passed all the building codes with risk, with safety factors. I'm sure that they did, but when you build super tall buildings, there are a lot more uncertainties that you have to take into account. And one of the things that very present in building design is the fact that you really have to take into account extreme loading scenarios. You can't make a design decision or an engineering decision based on expected behavior of the thing you're supposed to build, especially when you only get one chance to build it. You need to somehow look at these maybe low probability but very high consequence events, and we do that by using risk measures. So in this talk, a risk measure will be a lower semi-continuous functional on a space of random variables. And I'm going to add a condition that's not always there, but from my point of view, I don't care about any risk measure that doesn't have this condition. And that's that it should map constants to themselves. Is called translation invariance. So in this talk, the most important, there are many properties of risk measures that people study. Thomas knows them much better than me. He's given talks just associated to this subject, and I could do so as well, but I just want to encapsulate all into one slide. In this talk, there's two properties I really care about: monotonicity and convexity. There are many others, but I know I'm getting low on time, so I'm going to skip them. Do I?
Time.
Am I?
Yeah.
Oh, okay.
Don't rush.
All right. Well, even still, I don't feel like going. I could get just stuck here. So let's just leave it to the top two, and then we get a conversation.
The last one
offline.
should be strictly greater than the expectations.
Oh yes, you're right. Actually, I pointed this out to someone else. Okay, yes, you're right. Thank you. Thanks, Tom. Strictly greater here. That's right. Or because expectation is not risk averse. That's where the definition comes from. Okay. So if you have monotonicity and convexity, the reason why it's helpful or intuitive, why I like it so much is that it gives you nice properties in the underlying optimization, in the problems that you would hope would have nice properties. So in a tracking type PD constraint optimization problem, the underlying deterministic problem has existence uniqueness of solutions. One would want that the stochastic problem also does. And if you are monotonic and convex, then this property is inherited. So an example that you've already seen of a risk measure is the expected value. It pretty much satisfies all of the nice properties except for risk averseness, as Thomas pointed out. Another one that that's very intuitive, people use, is the mean plus standard deviation. One of the things I want to point out, though, how it's not monotonic or positively homogeneous. So it may not actually give you existence of uniqueness in problems where you would think that it should. Third one, conditional value at risk. This has monotonicity and positive homogeneity and two other nice properties, which together give you something called coherent, which is something will be exploited later. And then there are several others. So mean plus semi-deviation, the entropic risk, entropic value at risk. This topic, I'm going to just focus mostly on the first and the third one. However, because the second one is so appealing, I have one slide dedicated to it to just tell you in an intuitive way, beyond this being a mathematical statement, that it doesn't give you existence uniqueness. What's another feeling you can get for why you might prefer to use something else. So the standard deviation is the issue here, and the issue is because it measures the variability in the objective in a symmetric way. And in a lot of problems, you care about variability at some one end of the distribution and not the other. So if thinking about the building, we care about large loading scenarios, not small loading scenarios. So if we have a lot of variation in the small loading scenarios, that's great. We don't really want to penalize that type of behavior. We want to penalize the failure states. These extreme, the tail of the distribution into this sort of failure regime, just sort of one side of the distribution. And you think about it that way, it would be nice if you actually had a risk measure that did exactly that. And it turns out that that's, if there's no atoms in your distribution, that is exactly what the conditional value at risk does. So it is the expected value of your random variable past a certain quantile. So the quantile, if you were to integrate the PDF of your variable to a certain point and stop when the integral becomes beta and look at how far you got, that would be your value at risk of the quantile of beta. And the CVAR is the expected value beyond that point. So this is heavily used in investment banking. It gives you access to that tail, the specific part of the tail that you care about. And through this nice formula here that comes from exploiting the properties of this function, you can write it as an optimization problem itself. So if you optimize over a single variable, you can write it as expected value or as expected value optimization problem over an inflated space. So you would, if you have constraints, so it would be of C cross a single line. And then because this is an expected value problem, one could hope that some of the ideas that were fleshed out for adaptive sampling for expected value optimization problems work here. And that's generally what we have done, and we've seen good results doing that. So turning to this problem that you saw early on in the presentation, where we have uncertain load and uncertain thickness, and we're trying to find a stiffness optimizing steel shell, showing what happens when you optimize in expectation. You get pinching in the middle and this growth at the top. However, if you dial up your risk preference using the CVAR, I think this here is for beta equal to 0.9, you can get a very different type of design. And I'll put these three side by side, and then I'll try to explain why this is the case. So the third on the far left is showing what would happen if you just used the mean force and the min E material and did the deterministic optimization problem. You get extreme pinching in the center. The risk neutral case is a little bit more conservative, and the risk averse case is completely different. And the reason this is because how we set up the problem. So if I go back and actually show you the distribution of forces visually, the opacity of this arrow is meant to represent the probability of the force sort of appearing at those different ends of the structure. So there's a low probability that we'll see a force applied to those ends, but those are the forces that are going to impart the largest strain or stress on the structure, because there's less support at the end. So there's no support at the ends, and it's very close to the end. So if you're optimizing for the CVAR, you end up kicking out most of the middle loads. They don't even enter your optimization problem, and you optimize basically just for those forces at the end. And in order to accommodate those, you end up getting a very different shape at some point than if you were to just average out all the forces you should be doing here, or average out the effects of those forces on the objective function, which you see in the middle. So we can apply adaptive sampling to solve this problem. Adaptive sampling doesn't need to know the risk preference. It will figure out on the fly the number of samples you need to solve the problem right from the beginning, and then adjust the size of the sample set on the fly as you go. And you'll see, as one would expect, more samples, the more risk averse you are. And then finally, we're going to take all of this infrastructure and apply it to a building design optimization problem. We're trying to minimize the forces acting on a building. So the setting here, build up how we came about looking at this, is that modern day high-rise buildings, if you look around, you go to London, or I think even downtown Oslo, you see very, very fancy looking glass buildings, twisted buildings, tapered buildings with all these different types of very intricate levels. And it turns out that people were building these aesthetically pleasing designs and putting them in wind tunnels. They found out they had better properties than simple building designs a lot of the time. And the reason for this is, you think about the simplest building design, I would say, is think about one of the Twin Towers or something. So a rectangular square base, just extended uniformly upwards. Wind passes by this building, and this is going to release vortices, okay? And the vortices are going to be released at a certain frequency. And if you have the same frequency along the entire length of the building, this is going to sort of end up rocking the building side by side, like kind of pushing a child on a swing with that frequency. And actually, the Twin Towers were famous infamous for how much they shook back when they were around. And a lot of those simple buildings have this problem, and people do all sorts of things to try to mitigate this effect, because clearly you cannot sell office space or apartments, people don't want to be in a building that's constantly moving. So there are factors that people control. There are building codes. You can't actually have a building that those things. So you can't sell it. They're also hard to maintain. Things will crack. Windows will pop off. They have this. So it's a huge concern. So when people sort of, design these other types of buildings, twisted buildings, tapered buildings, put in the wind tunnel, and they found, oh, actually the loads are different. The reason realized is that vortex spreading pattern is disordered. You have different frequency at different heights of the building. So this has led to most modern high-rise buildings have some sort of non-trivial geometry built into them. But up until a couple of years ago, when we started studying this problem, we had never seen anybody do a mathematical characterization of this. Actually said, well, what would be an optimal building or a geometry to try to really optimize these loads? It was mostly a trial and error approach used by the industry. So here is our attempt to do this. We focus on the bending moment at the base of the building. This is the type of thing that would cause a building to tilt. So if you think of the Millennium Tower, if the bending moment's really high, the foundation is going to shift, and the entire building is going to twist. So we want to minimize some measurement of risk of the bending moment. So we're going to look at the expected value of the bending moment and the conditional value at risk of the bending moment with uncertain wind coming in. The design space is given by a CAD model, which accommodates tapering of the building and twisting of the building, which are two of the most common types of designs that people use in the industry. As well, we're going to take site-specific data. So this data comes from Basel, Switzerland, but in cities all over the world, including Oslo, that collect data and have been it's very common. It's been done for decades. Most cities average wind speed and direction data for different sites around the world. So if you actually incorporate that into the design process, what this would allow us to do is sample from this distribution and run simulations with the exact type of mean wind speed and direction for the building at the site which it's being built. So we do that. And then for one of those sampled speeds and directions, we run a large eddy simulation in this large box around the given building. We simulate this for, I think it was about 3.5 minutes of flow through this numerical wind tunnel, and compute the time series of the base moment for the given sampled wind speed and direction. So this is, of course, very expensive. So we want to reduce the number of samples as much as possible, because that's the limiting factor in the cost, or the first major cost to be addressed. So we do that through adaptive sampling. And you can see in these two plots on the right, the first one's for the mean, second one's for the C-var. Sample size is in blue. It chooses the right sample size it needs at the beginning and increases it gradually throughout the optimization process in line with the decrease in the objective function, which is given in red. So this is just engineering data I'll list for you, that the minimization of the mean reduced the objective function value by only 7%. However, the reduction in this conditional value at risk from a naive design was much more significant and close to 20%, which is quite important from an engineering point of view with respect to the C-var. And as I've told you before, when I said this is a $60,000 if statement, in order to actually implement this, we took stochastic gradient descent on this problem with a special if statement that we had proved these properties about. And then I think, I don't know why I say 25, it's $60,000 here, which is leading to 2.5 million CPU hour computation over the whole optimization loop. So here I'm showing the sequence of designs for the CVAR problem, and then showing the windrows with the initial design, a little bit of twisting, just a circular roof, and then the final risk neutral and risk averse design. And then here are the time series for the optimized designs. So the initial design showing the mean, the CVAR, and then we're seeing the mean value optimization obviously decreases the mean, CVAR does as well. What I want to point out here is that lower means better. Lower means more less lower base moment. And the CVAR is having the densest low values. It has the least probability of those extreme loading scenarios as it should.
The scenarios, were they used in the optimization or were they out of sample?
They were used in the optimization.
And
so
did you try it out of sample to see what happens?
Afterwards, yes, afterwards we did that. That's not shown in these slides, but it is in the paper. So once we find the design, we like oversample for the specific designing and can do some comparisons. Yeah. So we're almost at the end here. I'm going to summarize what we've done so far. The various adaptive sampling methods in the ongoing work into other types of stochastic optimization problems showed the statements of the theorems, not actually showing you the proofs that give you the optimum convergence rates in expectations for those algorithms, and then various applications shape topology optimization. Now the slide I want to end on is just a take-home message slide, way to conceptualize these things. A lot of the work I do deals with adaptive numerical methods. I got my start looking at adaptive finite element methods, adaptive mesh refinement. A lot of people study other types of adaptive methods, sidestepping, multi-level methods. This idea of adaptive sampling is just another element in this ecosystem of adaptive numerical methods, which all fit together. So a very efficient computer implementation would probably use many of these things at once. And efficiency and high accuracy in simulation comes from thinking adaptively. So I encourage you all to do so, not be afraid of adaptive numerical methods. And that's my talk here. Yeah.
Questions from the room or online? You could either post them in the chat or just turn your mic on. Oh no, don't turn your mic on because my mic isn't on, so maybe just use the chat. Okay, then I'll start. So CVAR is not smooth, but your updates, your adaptive scheme requires gradients. So what do you do there?
We used your trick of smoothing the CVAR.
Which one?
The first one in your paper with Drew from 2015, I think.
So the kernel smoothing.
Yeah, that's right.
Okay, because you need more than one derivative, I guess, or
you only need one derivative.
You only need one derivative.
Yeah,
okay.
We only looked at first order methods here.
Okay.
Yeah.
And what happens if you let that smoothing parameter decrease? And also adaptively, sort of in the method, does it require then all of a sudden more samples, or did you check that to see what? Yeah.
We did do this. So this started as a master's thesis project where we were doing a bunch of different exploration with that. I forget the conclusions that were written up in the thesis, but it didn't work so well.
Yeah, I would expect it would.
Which we weren't expecting it to.
Yeah.
Yeah. So one could imagine like a doubly adaptive algorithm where you adapt the smoothing parameter and adapt the samples. And you can adapt all sorts of things simultaneously. But we didn't really explore that.
So the screen went out again.
Yeah.
And then another question would be, all right, gone.
Another thing I want to just say before we get to the next question, we did recently look at doing adaptive sampling for the primal dual approach you and Drew wrote about recently.
Yeah, that would be interesting to see.
Yes.
Because we don't have adaptivity for that.
I don't think it will work. Yeah,
Maybe.
it wouldn't be efficient, so
Yeah.
we can totally talk offline for
Sure,
why it sort of fails. But yeah, we're not entirely satisfied with the fact that we have to regularize the objective function from a mathematical point of view. But when I talk to engineers, they don't care. Because, and I think this is worth saying, like very clearly, is that a lot of these problems have systematic uncertainty that you just cannot just model away or sample away, right? So there's going to be error there that allows you some wiggle room to maybe, modify your objective function a little bit, as long as the modification is not commensurate with the amount of error that's just, in the underlying problem itself.
Yeah, I mean, the smoothing approaches have theory, right? Like they tell you, you'll converge back to the original problem. You can get convergence of minimizers and so on. So that it's not like it's just, a heuristic. But so if you go back to the estimates that you guys derived, I mean, I suppose the risk of giving away a research idea, you could.
This one, or do you want the
where's the bound? Yeah, I mean, like here, for example, or just before, like where you define the capital R.
Yeah.
So you do this because you want to project onto the set, but I guess you could also probably develop a very similar approach where you have sort of a smooth function and a non-smooth. You can calculate a prox operator, and you could probably do exactly the same thing. So you wouldn't have constraints.
Yes.
You wouldn't have a projection, but you'd have an operator with the same property.
That's right. So actually, that has been done. So that's the other. I said that there are two papers that came out. Recent at almost simultaneously. So that was the other novelty they had, is that they looked at a composite optimization. All right, so it's been done. Yeah. Okay. But there are lots of things that have not been done. Actually, I think this field is ripe with open problems of great importance.
Yeah, I mean, another one was you had this expectation constraint.
Yeah.
So I have a preprint with Drew Corey and Matthias Staudigl on basically the strongly convex case of that one. Yeah. Right, where we use an expectation approximation of a probabilistic constraint. And we have a first order method with convergence statements as well in Hilbert space. So I mean, if your result works for this type, then I could give you also an algorithm that you could try that on. It might be interesting to see. I would be very interested. So we're second year of a 3-year project, mostly dedicated to adaptive sampling, and eventually we're going to. Yeah, I can give you a first order method for that. I mean, we also did augmented Lagrangian, and it's better. Okay. But, we have no theory for it. So the first order method has convergence guarantees. Okay. Yeah, we should talk. Sure. Yeah. Great. Rami.
So in theory, you have these tests, right? But in practice, you have approximations to them.
That's right.
So do you know of bounds comparing the two, the actual test and the approximate ones?
So there are some probabilistic bounds you can work out if you make some assumptions. I mean, the first assumption is you need a bounded variance, but sort of that's already built in since we're trying to control the variance and the gradients. And if you have that assumption, you can relate the expected value to some probability of violating, like a expected value constraint that you're averaging to a probability that you're violating that constraint. That's one way you can analyze this. There's some other recent work that's been done only in the unconstrained setting, analyzing the practical algorithm. But generally speaking, if I want to say one just universal and true statement, is that that type of work is just getting started to completely understand the practical algorithm itself.
If you have such bounds, then can you have the theory in terms of the practical bounds only? Or
I think you could, but it would take additional work.
Okay.
Yeah.
Have you looked into the adaptive sampling and machine learning problems?
Yes. So the collaborators of us mostly look at those types of problems. I'm not convinced that that's the ideal setting for this type of technology. But they do have some promising results there, but I'm not an expert on them. Yeah.
Anybody else? Anybody online? Okay, then let's thank the speaker again. You want to